the 2 warm-up questions. What's the definition of probability? So what's the fundamental definition? The definition of probability is?
Once out of outcome, something like that.
Yeah, what you want to happen out of the total number of things that could happen. Yeah, once out of total. And another word for total is sample space. And then another word for what you want to have happen is the event that you're describing. So there's a particular event that you want, and then the sample space is all the things that could happen. So that's the definition of probability. And then we learned various ways of counting things, and we'll learn more ways of counting things today, so that you can count how many objects are in there, how many objects are in here, and then you can calculate the probability. Next, what's the fundamental counting principle? This is what Simone loves so much. The fundamental counting principle. So, like, let's talk about the number of outfits you could make in your closet. So you have some number of pants, you have some number of shirts, and you have some number of shoes. And so how many distinct outfits could you make? Like, let's say that you have 3 pants. I don't know if that's a lot or a little. But let's say that you have 8 shirts, and then let's say that you have 2 pairs of shoes. So how many distinct outfits could you wear on any given day of the week? And how do you do it? You just multiply straight across. So that'd be 48. And that's the fundamental counting principle. You jot down the total number of possibilities for each decision, and then you multiply through all of those decisions. Okay, so we got through a certain distance last time. Oh, let me just review where we are here. So today's February 21st. We will finish chapter 7 and start chapter 8. And then we have another class period next week, and at the end of next week on Wednesday, we have our test. So just note that we'll have a little bit of time at the beginning of the class period to review, but then you'll take your test. Next week? Yeah, next week. Yeah. And then, what else? Then we'll review for the final exam and then take the final exam. Okay. I've got 2 jokes for you. What do you call a number that can't keep still? A Roman numeral. Wait, what was it, Joe? Roman numeral. What do you call a number that can't keep still? A Roman numeral. Okay, what about this one? I think this is cute. Why did the student wear glasses to math class?
Because I can't see.
It helps with division.
Oh.
It helps with division. Division. Helps with the vision. Okay, well, anyway, there we go. All right, so chapter 7. We got to about here. And I realized as we read this question, I didn't even like this set of questions. So let's just be done with those questions about mutually exclusive. Mutually exclusive means that they cannot happen together. So moving on, I chose certain select problems that we're going to do, and we'll cross out the rest. Okay? So everybody, as we move through the rest, where are we on number 60? I've circled some of them, and the other ones you can cross out. So, everybody ready? We are going to do 61 and 62. So the first thing I want you to notice in all 4 of these problems is a new word, which is the word or. Where's the next one? Or. There you go. Even in number 62, it says find the probability that a sum of at least 10 when 2 fair dice are rolled. That means a sum of 10, 11, or 12. So anytime you have a probability question and they give you an or actually implies that you are going to add probabilities together. So you're going to calculate multiple probabilities and add them all together. So for instance, in number 61, it says, find what is the probability that a sum of 6 or a sum of 10 is obtained. Now, to even think about this problem, you need to remind yourself about that image that I had of the sample space of dice. So let me type that in real quick. Sample space dice of 2 dice. Hopefully it just pops right up. There it is. We'll make that bigger. Go. Put that over there. So folks, what is the probability that a sum of a 6 or a 10 is rolled? So first of all, which of these add up to 6? That one, that one, that one, that one, that one. And then which ones add up to 10? 6 and 4, 5 and 5, 4 and 6? So those are two separate questions. The first question was, what's the probability that a sum of 6 is obtained? So what's the probability for a sum of 6? 1, 2, 3, 4, 5. So there's 5 out of 36. And then what's the probability that a sum of 10 is obtained? That's 1, 2, 3, 3 of those. So that's two separate probabilities, and then you add them together. Oh, 3 out of 36. There we go. So the probability of getting a sum of a 6 was 536. The probability of getting a 10 was 336. So the overall probability of getting either of those is 8 out of 36. And by the way, when you put your answers into my math lab, you always have to simplify your fraction. So I think this is both divisible by 4, so that's 2/9. All right, key idea here is that OR means you're going to add probabilities together. So like in number 62, we're just doing 61 and 62. Find the probability that the sum is at least 10. So that means you can have the probability of 10, or rolling a 10, rolling 11, or rolling a 12. So what are those probabilities? The probability of rolling a 10 is 3 out of 36. And then the probability of rolling 11, there's only 2 different rolls that could add up to 11. That's the 5 and 6 and 6 and 5. So that's 2/36. And then the probability of rolling a 12, a sum of 12, there's only 1 pair of dice that would do that, the 6 and the 6. So you have these 3 probabilities that you would then add up. Now you might feel like, that seems a little artificial. I mean, if I just wanted to ask, what's the probability that the sum is at least 10, I would have just counted them all. I would have said 1, 2, 3, 4, 5, 6. There were 6 of them. But this demonstrates that you can find each probability separately and then add them together. So 3 plus 2 plus 1, that's 6/36, which adds up or simplifies to 1/6. Yep. So if you see the word OR, you're calculating many probabilities and adding them together. Questions about that part? Simone, what was your question?
I don't know.
Oh, okay. I thought you had a particular question in your eyes. All right. Then let's. Okay, in this one we're just going to do number 65.
So skip 63 and all that.
Yeah. Ah, yeah, this is fun. So in number 65, I should keep my sample space out so we can all see it. There. So in 65, it says when 2 balanced dice are rolled, there are 36 possible outcomes. We know that. Find the probability that the first die is a 3 or that doubles are rolled. So you have that word or, so we're calculating 2 separate probabilities, and we're going to add them together. Both probabilities are out of 36. And these are 2 separate events. So what's the first event? The first die is a 3. So how many outcomes do we have where the first die is a 3?
6.
Yeah, we've got 6 possible rolls where the first one is a 3. So we can go ahead and say 6. Now, the other event is that, oh, here we go. Oh, I wrote that up. It should technically be on here. 6 out of 6. Second question is, or that doubles are rolled. Well, where are the doubles? So we have to look very carefully here. We're looking at those pairs of dice that are along the diagonal, right? So the 1 and 1, the 2 and 2, the 3 and 3. Now we want to count all of those. The thing we have to be careful about right now is, first of all, how many doubles are there?
6.
Also 6. But if we count 636 plus 636, what would we be doing incorrectly? Yeah, we're counting that one twice. So we have to be really, really careful that if you have overlapping events, that you count very carefully and look for anything that was overlapping. So we did have one overlap, and that one overlap represented 1/36. That was one event out of 36 that was counted twice. So you can either subtract it out, subtract out the overlapped one, or you could have just counted everything by hand. You could have just said, well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Or you could calculate both events separately and then subtract out any overlap. So I subtracted the overlap. And what are we left with? 1136.
Are we allowed to have, show that the dice sample space?
I'll have that on the test.
Oh, don't believe, thank you.
Oh yeah, you're welcome. Or you can just draw a picture of it real quick. But yeah, I'll give it to you on the test. Okay, any questions about that idea? Then let's try another one. The next one I want to do with you is number 67. So you can circle 67. So now we're going to talk about odds. Okay, so this is a different idea than probability. Have you ever heard of talking about odds? Like, what are the odds that something would happen? Well, when somebody says, what are the odds? And, you know, let's just say that you're flipping a quarter and you're wondering, what are the odds of getting heads? It would not be correct to say, what are the odds of flipping a coin and getting heads, and still saying 1/2. Because 1/2 is the probability. And odds and probability are two different concepts. So when we talk about probability, everyone take a look here. Probability is looking at what you want to happen out of the total number of things that could happen. Whereas when we talk about odds, we're creating a fraction of what you want to happen compared to what you don't want to happen. Which is kind of cute. Because after all, this total, the total is all the things you want plus all the things you don't want. So what we're really doing is we're just changing our denominator to focus on the things you don't want to happen. Okay, is that fair that the total number of things consists of all the things you want and all the things you don't want? And there's nothing else. There's no third option. Like, oh, that's something I kind of want. No, it's got to be things you want or the things you don't want. So when we calculate probability, it's want out of total, but when we calculate odds, it's want out of don't want. To be fair, it's a ratio. Okay, this one is a proper fraction where you can, the fraction will always take in a value between 0 and 1. But odds, the numerator will sometimes be bigger than the denominator, and that's okay. So technically speaking, odds is more of a ratio. And maybe any of you have gambled or watched movies on gambling where they say like, oh, I'm watching the horse race, and the odds of that horse being that horse are a 2-to-1 ratio or a 2-to-3 ratio. Or they say, I'll take those odds. Anybody? I mean, I don't gamble or anything, so I don't know. But let's go ahead and try this. Find the odds in favor of spinning an A on the picture below. So when we say find the odds in favor, then what we're doing is we're creating a ratio. So here's odds. We're creating a ratio of in favor, what you think is in favor, out of what is out of favor, what you don't want to happen. Okay? And that's slightly different words. Want out of don't want, favor out of favor. So what's in favor? What do we want? We want to spin an A. So how many A's are there? 3. Yeah, 1, 2, 3. And then what are all the events that are out of favor? Well, everything else. So there's 1, 2, 3, 4, 5 other things on there. So those are the odds that we just computed. The odds are 3 to 5. You can write that as a fraction, or you can write it as a colon. The odds are 3 to 5. So you have 3 options in your favor and 5 options not in your favor. That's what odds mean. So if you take a look now at the answer key, I wonder how they're going to give it to us. 67, 3 to 5. They write it strictly not as a colon, but they actually say 3 to 5. That's how they say it. It's 3 to 5. So there's 3 things that could work in your favor, 5 things that don't work in your favor. What's that, Elizabeth? Oh, okay. Okay, so that's the odds. Should we try another one? But just for fun, let's try number 69. So everyone, let's do 69. Find the odds in favor of drawing a red marble when the red marble is selected at random from a bag containing 2 yellow, 5 red, 6 green. So in this bag, we have 2 yellow, 5 red, 6 green. And we want the odds in favor of drawing red. So what we want is red And what we don't want is anything else. So we have a total of 5 red. That's in our favor. And how much does everything else add up to?
8.
Yeah, 8. So the ratio, or the odds, would be 5 to 8. And so when we express odds, again, we're literally saying how many things could go for you and how many things could go against you. So those are not good odds, right? Only 5 things that will help you and 8 things that will hurt you. Okay, well that's the definition of odds. Does anybody like the idea of odds rather than probability? What would you rather someone say to you? Like what if the odds were actually 1 to 1? So there's one thing that'll work for you, one thing that'll work against you. Would you rather someone come up to you and say, the odds are 1 to 1? Or would you rather someone come up to you and say, you have a 50-50 chance? You have a 50% probability. What sounds more compelling to you? 1 to 1 or 50%? 1 to 1. Really 1 to 1? Yeah. I mean, it's what, it's just 2 different ways of communicating the same idea. Right. Let's try some data tables. I would say these data table problems are some of the more important ones because this is typically how information is communicated, is in a bunch of tables. Alrighty. We are going to do number 71. Now keep in mind, folks, even though I'm only doing certain ones of these, and I'm not going to grade you for the other ones, you can do them.
Extra credit.
No. Extra credit for your brain. Yeah, extra credit for your brain. Okay, number 71. Below is a table of data from a survey given to 1,600 teenagers, asking them to estimate, mind you, what % of their classmates are using drugs. Now, this is a very interesting question in and of itself. You're just asking them, and you're like, hey, how many of your classmates do you think use drugs? And they're like, 50%. Right, so I mean, what is this survey really telling us? Is the survey actually telling us how many people are doing drugs? No, it's merely giving the perception, right? This survey is telling us how many classmates people perceive are doing drugs. So like, let's just look at the boys. So out of the boys, only 24, hold on a second. Let's add up those 2 rows real quick. I think we need to add up those 2 rows so we know how many boys responded and how many girls responded. Because I wonder if they ask the same number of each. That would be a good survey. You'd want to ask the same number of each. Right? And yes, it was 800 boys and 800 girls. So out of 800 boys, only 24 of them said nobody's using drugs. Whereas there were more girls who said nobody's using drugs. Whereas, oh, I wonder how it compares all the way across. So the boys said, oh, 1 to 24% of my peers use drugs. 183 boys said that. 233 said that for girls. And then boys, 450 of them responded that 25 to 49% of the students use drugs, and so on. So anyway, that's what the table is saying. So the question is, if a girl is selected at random, so first of all, we're choosing a girl. Find the probability that her estimate of the percentage using drugs is 50% or higher. So that's the number of girls who said 50% or higher. But the key thing is that we're only strictly looking at girls. All right, so if a girl is selected at random, find the probability that her estimate of the percentage is 50% or higher. So when we talk about probability, what this problem is doing is changing the sample space. It's changing the total. So even though we actually know there's 1,600 teenagers of boys and girls, they're actually asking us in this problem to reduce our sample space to just the 800 girls. Okay, does that make sense? So we're not talking, the total is not the 1,600 boys and girls. The total is just the 800 girls, and we know that because it says if a girl is selected at random, so we're only looking at the girls, then find the probability that she would say 50% or more. So then we add those 2 numbers together, 166 plus 7, and that would be our probability, which is 0.2163. new concept that we're seeing here is this idea of changing the sample space. That is, narrowing down our sample space. That instead of considering the whole sample space of all 1,600 boys and girls, we're only looking at the sample space of the 800 girls. Traditionally, you know that you've narrowed down the space if you've used the phrase given that. So for instance, the problem could have started by saying, given that you only ask girls, that would have been a traditional way of telling you that we just reduced our sample space. How does everyone feel about that? All right. So far we've seen a couple key phrases. Or means that you add probabilities, and given that typically means that you reduce the sample space to a smaller sample space, meaning your total just got smaller because you're only looking at particular people. Okay. The next question shows is number 73. I need a utility belt like Batman. I can have my eraser, my mouse, and my markers. That would be awesome. Okay, number 73. Now, all of these problems, you'll notice, are now telling us the odds. So like look at this first one. It says the odds in favor of winning a horse race are 7 to 2. So that's odds in favor. So 7 ways you win, 2 ways you lose. So that's what it means that it's in your favor, or specifically it's saying the odds in favor of a horse winning. So the 7 is 7 ways you win and 2 ways you lose. Now find the probability that the horse would actually win. So remember, since odds are want to don't want, then by adding those 2 numbers together, that gives you the total number of ways something could happen. So the total number of ways that something could happen right now is 9. So our probability is simply want out of total. And what we want is the 7, and the total is 7 plus 2, which is 9. So that's how you convert an odds problem to a probability problem. It is not overwhelmingly exciting or hard. It's just, if somebody gave you the odds, then you could convert it to a probability. Let's just do one more here. I like number 75. So we did 73 and we're doing 75. The odds against Carl beating his friend in a round of golf are 6 to 5. So notice this says the odds against Carl beating his friends. So that means 6 ways he loses and 5 ways he wins. So you notice that we labeled that backwards from the first one, because these are the odds against him winning. So 6 ways he'll lose, 5 ways he'll win. Now find the probability that he'll win. So what we want is for him to win. And how many ways can he win? 5. And the total number of things that can happen is 6 plus 5, which is 11. Okay. All right. Let's do the next couple problems here. Number 76. If a single fair die is rolled, find the probability of a 4 given that the number rolled is odd. This is a great example of the phrase given that. So given that is reducing our sample space. Normally a die has 6 sides, but because of the given that phrase, we're only looking at a sample space where the number rolled is odd. So how many odd numbers are there on a dice? How many odd numbers are there on a dice? 3. You have 3. You got 1, 3, and 5. So our sample space just reduced to 3 instead of 6. Even though there's normally 6 sides on a dice, the phrase given that the number rolled is odd, we're saying, hey, we know for sure that the number that we rolled is odd. So it's got to be 1, 3, or 5. That's only 3 possibilities. So now, what's the probability that we roll a 4? If you know for sure that the number you rolled is odd, what's your probability of getting a 4?
0.
Yeah, nothing. 4 is not an odd number. So that's just 0. Okay, let's try a couple more given that problems. We'll do 77 and 78. So if 2 fair dice are rolled, find the probability of a sum of 6, given that the roll is a double. So probably the first thing we want to do is look at the given that. So that's our sample space now. How many doubles are there? On that big grid, how many of them were doubles, like a 1 and a 1, a 2 and a 2, a 3 and a 3? Do you want to see it?
6.
Yeah, well, yeah, 6. I didn't hear you. Yeah. I didn't hear you, Simone. Yeah, so there are only 6 of those that are doubles. So given that we're only looking at doubles, what's the probability that they add up to 6? How many of those doubles add up to 6? There's one of them, the 3 and the 3, right? So that's it. The probability is 1 out of 6. You'll notice that we changed our sample space. We reduced the sample space. And then we only looked within that sample space to calculate the top number. Right? You only get to look inside the reduced sample space to look for your event. Because there are a lot of other numbers that add up to 6. Okay, and I said 78. If 2 cards are drawn, okay. So you've got 2 cards from a deck. How many cards are in a deck again?
52.
Yeah, so you've got 52 cards in the deck. It says if 2 cards are drawn without replacement. So let's look at that phrase real quick, without replacement. That means I take 1 card off the deck, and what do I do with it? Then you don't put it back. I'm just going to keep it. I can put it in my pocket, I can eat it, but I'm not going to put it back on the deck. And then I draw another deck, or another card. So when I drew the first card, I was drawing it from a deck of 52 cards. But then when I drew the second card, I was drawing that card out of a deck with only 51 cards. So in the first draw, your sample space was 52. But in the second draw, your sample space was only 51, because you removed a card. So let's look. It says, if 2 cards are drawn without replacement from an ordinary deck, find the probability that the second card is a spade, given that the first card was a spade. So the given that means we're going to reduce our sample space. And so specifically, what does our deck of cards look like if we removed a spade? How many cards are in the deck?
52.
No, you removed a spade.
51.
Only 51. And how many spades are left?
12.
12. So there's 51 total, and there's only 12 spades. That's what's left after we remove a spade. So this is what we have now. And they're asking, find the probability that the second card is a spade. So right now, looking at that deck of cards, what's my probability of drawing a spade? 12 out of 51. Because that's my reduced sample space. I took a spade out of the deck. Does that work? Is that idea? Does that make sense? Okay. So again, that's what the phrase given that means. You're reducing your sample space. I feel like I should have told another joke. Like how class is going to be canceled in 20 minutes. No?
It's raining, so it might.
It is raining. Yeah, maybe we're all experiencing arthritis pain.
Literally, I can't laugh about that.
You can't what?
I can't not laugh about that. My joints be cracking.
Oh, are they?
Like, for real. I'm old.
No, what's wrong with your joints?
Like, it cracks. Like, when it's really
When it's
cold.
raining?
Yeah, like, not when it's raining, like, when it's cold.
Oh, okay, I got you. Okay, moving on here. Number 80. Let's go and do 80. Assume that 2 marbles are drawn without replacement. Now listen, I see what we're doing. We're going through a series of questions that are different probability scenarios, right? And we're just trying out different scenarios. So on the one hand, you might feel like, gosh, we're just kind of looking at question after question. But yeah, we're seeing how probability questions, depending on how they change depending on the situation. Okay, so we have drawing 2 marbles out without replacement from a box. So draw a box, and it has 1 blue, 3 white, 2 green, and 2 red. And what we're doing is we're saying, assume that 2 marbles are drawn without replacement. And it says, find the probability that both marbles are red. So what we're going to have is very much like the fundamental counting principle. We're going to create a bucket for each event. where you're going to draw a marble, take it out, and then draw another marble, and take it out. So let's look at the first marble that you draw, and then the second marble that you draw. What's the probability that the first marble is red? 2 out of 8. So that's the probability that the first marble is red. However, now we have to reduce the sample space and say, well, I just took that red marble out. So now what's my probability of getting another red marble?
1 out of 7.
1 out of 7. Exactly right. And you can just look and see what happened to the numerator and what happened to the denominator. I subtracted 1 from each because I'm reducing my sample space because I removed the red marble, and I'm reducing the numerator as well because I have less red marbles now to choose from. And so now you multiply straight across and you get your answer. So I would simplify the 2 8s first. The probability of getting 2 reds is 1/28. That was over 80. Let's try 82. Yeah, 82 is clever. So, looking at 82 now, it says, again, assume 2 marbles are drawn without replacements. So you're going to take one out and then take another one out. And we have 1 blue, 3 white, 2 green, and 2 red. Now this one's tricky. Find the probability that one marble is green and the other marble is red. Okay? Yes, Josue?
Probably not understand why you multiply the 2 numbers for number 80. But for 78 seems like a similar problem.
78 seems like a similar problem. And 78, wait, 78?
7.
Oh, right. So first of all, in number 78, it had the phrase given that. And so that means that wait, what are you comparing to? You're comparing number 80
Yeah.
to number 78. We multiplied probabilities in both of those. We didn't even do 78. Did we do 78?
Yeah. You got 12.
Oh, right. Yeah, in 78, we didn't multiply anything. We just looked at the second probability.
Why did you multiply this one then?
Well, because in this one,
They're asking the same thing.
yeah, okay, thank you. In this one, they didn't say given that. They didn't say given that the first one is red, calculate the probability the second one is red. Because if I said to you, given that the first drawing was red, then that just creates a new sample space. And now they're just asking a question about this alone. In this one, 2 probabilistic things had to happen. First, you had to calculate the probability that you grabbed a red. And then you had to calculate the probability that you grabbed another red. In the previous problem, they used the phrase given that, which means given that this is already what you have. Somebody already took the red one out, forget about it, it's done. So now just calculate the probability of getting a red. It'd be 1/7. So the phrase given that is very powerful. It means forget what already happened in the past, it's already done. Now just calculate your probability based on what's going on right now. Josue, does that respond to your question? Does it really? It really does? Okay. Okay, so then which one are we on now? 82. So, in number 82, they're saying find the probability that one marble is green and one marble is red. Here's what makes this question tricky. What could we do here? It could be that the first thing we do is draw a green one and then a red one. Right? Is that one possibility? Because they want us to draw a green one and a red one. So it could be that first we draw the green, then we draw the red. Or it would be just as fine with us if we grabbed a red one and then a green one. Because either way, we ended up with a green one and a red one. And so the problem is implying the use of the word or by saying, hey, I just want a green one and a red one. It doesn't matter to me how you get it. So it could be that you draw the green first, then the red, or it could be that you draw the red first, then the green. And so the word or again means plus, and we're going to end up calculating 2 different probabilities for each of those events and then adding them together. So let's do the first one first. What's the probability of getting a green one? That would be 2 out of 8.
And then you take that out, remove it, now change that to a 1. And now I want to know the probability of getting a red. That's 2 out of 7. So that's the first event. Now I need to go back, make my sample space normal again, back to the way it was. Now calculate the probability of getting a red one first, which would be 2 out of 8. And then, so I removed 1 red one now. And now calculate the probability of getting a green, that'd be 2 out of 7. Now you'll notice that the numbers ended up being the same. But the key thing is that those were, in fact, 2 different ways of drawing a red and a green, because the green could have come first or the red. Okay, so now we simplify. So that's really 1/4. And this one's really 1/4. And so the first fraction is 2/28. Right? Plus the second fraction is also 2/28. And so if we add them together, that's 4/28, which that can be simplified by dividing them both by 4, and we get 1/7. So the overall probability of drawing a green one and a red one, in which it doesn't matter which comes first, is 1/7. Plus, Wade, your question is a really good one, because these are different probabilities and added them together. In this problem, we actually did calculate the probability of the first event and the second event, whereas in the one you mentioned, 78, there was only one probability to calculate in the first place. And it all boils down to, so far, these keywords or and given there, telling us what to do. Wade, do you have a question right now? No, you're okay. All right. Hello, everybody. Let's keep going. I would like us to do number 83 and 84. So it says if 81% of scheduled flights actually take place. So that's one thing, is that only 81% of the time will your flight actually leave. Should we just say on time or leave at all? And it looks like they're saying 81% of scheduled flights actually take place. So only 81% of the time does a flight actually leave. And cancellations are independent, meaning that if the first flight cancels, that has no bearing on whether or not the second flight cancels, and that has no bearing on whether or not the third flight cancels. So it's saying, what's the probability that 3 separate flights will all take place? So we have 3 events. We've got the first plane, the second plane, and the third plane. And the probability of each one of those happening is 81%, which we write as a decimal. Just like in finance questions, we talk about interest rates, like 5%, but we do everything in decimals, 0.05. Also in probability problems, we always express everything as a decimal. So even though they say 81%, we turn that into a decimal, and then we multiply that straight across, and we get 0.531. So just imagine how terrible this is if this was reality. They're saying that if you had to take a 3-flight adventure, like today you're going to leave Phoenix, and you want to fly to New York, but the only flights available go from Phoenix to Las Vegas, and then Vegas to Chicago, and then Chicago to New York. First of all, would any of you enjoy having 2 layovers? I don't know, maybe not. But what they're saying then is if you really did have 3 flights to get to where you were going, you've really only got like a 50% chance of actually getting there today, because one of those 3 flights could have been canceled. Okay. Anyone? Everyone's happy? It's the day you're happy. Oh, good. It's out of you. Oh, damn. Hey, Cheryl. How's it going? Okay. All right, let's look at 84. So if 2 cards are drawn with replacement, everybody underline, with replacement. What does that mean? So you take a card off the top, you look at it, and then you put it back in, and you shuffle the deck up. So with replacement means I'm going to take one out, put it back in, take one out, put it back in, and that means the sample space never changes. Your sample space stays 52 cards every time. So let's look at these 2 events. It says find the probability that the first card is a heart. So that's my first event. I want to draw a heart. And the second event is a diamond. Where did Simone go? You know what I think I should do is take all of her stuff in her backpack and hide it.
That'd be funny.
Is anyone on board with that? Does anyone think that's a good idea?
Yeah.
All right, so first of all, what's the probability that it's a heart? From the whole deck of cards, how many of them are hearts?
13.
Yeah, 13 out of 52. And if we remember that there's only 4 suits, the probability of choosing a heart would be 1 out of 4. So you can write 13 out of 52 because that's true. There are 13 hearts out of 52 cards, but that simplifies to 1 out of 4, which represents the fact that there's only 4 suits. So the probability of a heart is 1/4. And then you put that card back, and then you draw again. And what's the probability that the second one's a diamond? Also 1/4. So overall, your probability of drawing a heart, putting it back in, drawing a diamond is 1 in 16. Okay. Boom. We've got some exciting problems coming up here. You're all gonna really enjoy it. You're gonna say, wow, Mr. G, this is fun. All right, let's go to 86. Now, this is gonna involve some drawing. So draw it with me as I draw it, write it yourself so that you're caught up. It says here that 45% of a store's computers come from factory A, and the remainder come from factory B. So what we're gonna do is draw a tree diagram where we start right here, and the first choice is, do the parts come from factory A, or do the parts come from factory B? And as you travel along this tree, you're making certain decisions that have certain probabilities. And what they're saying is, which automatically tells us that the remainder comes from factory B. So 45% come from A, how many come from B? 55%. So already there's a 45% chance of going that way and a 55% chance of going this way. Then it says 5% of computers from factory A are defective. So we have another branch where now we're saying these are defective. And as opposed to writing not defective, can we just write okay? Those parts are okay. So now, 5% of computers from factory A are defective, so that's 0.05. So if 5% are defective, how many of them are fine? And 95%. Okay, then from factory B, 2% of computers from factory B are defective. That's 0.02. And then the rest are okay, which is 98% of. So everybody, I'd like you all to go ahead and take your calculator and go ahead and calculate each branch to see each reality. So for instance, if you go along the top branch, that probability is going to be 0.45 times 0.05. And then you type it in your calculator to get it. This branch is 0.45 times 0.95, and you type that in your calculator. This branch is 0.55 times 0.02. You type it in your calculator. And then that bottom branch is 0.55 times 0.98, and you type that in your calculator. This is called a tree diagram. So like this first one is 0.0225. Next one is 0.4275. And 0.011. And 0.5612. So the first thing you'll notice, all the probabilities at the end add up to. If you add up all 4 of those at the end, what should they add up to? What should they add up to? What?
100.
100. Yeah, 100%. It should add up to 1. So all those probabilities add up to 1, meaning you got the part from somewhere. Okay, which one of them, where do you have a higher % chance of getting a good part? Factor A or factor B, Luis?
Wait, I got 0.539 for the last one.
Good. 0.55 times 0.98. I also got 0.539. Thank you, Louise. And I suppose a self-check mechanism is to actually add them up. 0.539 plus 0.011 plus 0.4275 plus 0.0225. Yeah, okay, now those add up to 1. Simone, I just want you to know that they all told me that I should take your stuff and hide it, and I said, no, that's wrong. I don't think that's a nice thing to do to Simone or anyone. What?
The bullies.
Yeah, I know. Come on, folks. Be nice to Simone. Okay, so you can, using this tree diagram now, you can ask a lot of questions. You could say, what's the probability that you have a defective part from factory A? And that's 0.0225. What's the probability that you have a good part from factory B? 0.539. Like, if you just, now if you have all these parts and you just reach in and grab one, you can say the probability that it's a good part from B is 0.539. And the probability that it's a defective part from factory B is 0.011, and so on.
Sorry, will we have to change that to percentage form or no?
No, you can just leave it as a decimal. Okay. So this particular question says, what is the probability that it is defective and from factory B? So everybody underline that word and. And is a word that means multiply. Okay, so we've seen some very specific vocabulary that they use in these problems. Or means add, given that means reduce your sample space, and means multiply. So when they say defective and from factory B, that means you follow the branch for factory B, and then you go to defective, and you multiply those two probabilities together. So 0.55 times 0.02, that's simply what this branch is, and therefore the probability is 0.011. So the probability is 0.011. The probability that it is defective and from factory B is 0.011. Now before we leave this example, I want you to notice you could ask other interesting questions. You could just, and this is how we ask it, we say probability, P probability, parenthesis, defective. Just what's the probability in general that the item is defective? So what's the overall probability that it's defective? What would you do? Just the overall probability of it being defective means it's either defective from company A or defective from company. If it's defective from A or B, what would you do? Just add them together. So the overall probability that it's defective is 0.0225 plus 0.011, which is 0.0335. Or you could say the overall probability that it's okay, you can just add up those two branches. And that would be the overall probability that it's okay. One more really interesting one, and I want you all to write it down. What if I said, what's the probability that it's defective given that, no. There we go. What's the probability that it came from factory A given that it's defective? Okay, so this is a really interesting question. You can imagine yourself kind of wanting to like point fingers at the companies. So like you're holding this defective part in your hand, and you're like, man, I got this defective part. All right, that's given. It's given that it's defective. What's the probability that came from factory A or factory B? Now maybe you can already tell. Look at those two defective probabilities. Which one's bigger? That one. So more than likely it came from factory A. But there's a specific way of doing it. So look at this question. Given that it's defective, what's our new sample space? Because we're using the phrase given that. Our sample space is it's defective. So we'd add those two together. So those are all of our defective parts, so 0.0225 and 0.011. So the sample space now becomes 0.0335. And we want to know what's the probability that it's from A and defective. So it is defective and it's from A. And therefore, we're looking at this probability, 0.0225. That's a very interesting and different type of question. We're saying, given that you already know it's defective, what's the probability that it came from A or B? So now we do that computation, 0.0225 divided by 0.0335. And it's actually 0.67. So a 67% chance that if you have a defective part, it came from A, not B. And I just threw that question out there because it's a nice use of given that. Okay, well, 87 is another tree problem, so you'll be able to do that one on your own or when you see a problem like it online. Number 88 is also another tree problem just like it. So what I'd like to do then is 89. Yep. All right, in 89 it says, in a certain US city, 51% of adults are women. So let's start our tree diagram. It's either women or men. And since 51.4% of women, so 0.514, the percent that are men, 0.486. And you just have to use your calculator to subtract that from 1. Now it says, in that city, 13% of women suffer from depression. So women, look here, depression, DEP. Oh, that's funny. And the last problem is DEF for defective. Now this is DEP for depression. So I'll say depression and okay. So in that city, 13.4% of women are depressed, so 0.134, which means how many are okay? 0.866. Did anyone else get that? You can just do 1 minus 0.134. What do you get? Did anyone else? Did you get that, Luis? Wait, you did? Or are you still doing it?
No, I didn't do it.
Okay. And then 9.4% of men suffer from depression. So now down here for men, again, you have 2 branches, one leading to depression, one leading to being okay. And for the men now it's 0.094. And so the percent that are okay are 0.906. Okay, so does everyone have their tree diagram and understand how I made it? They tell you one of the decimals and you subtract from 1 to get the other decimal. Hey there, Don. How's it going?
Good.
What you watching?
ESPN basketball.
Oh, wow. And is your team winning?
I was just reading on Zion Williams.
Oh. I admire your honesty, Don. You could have just said you were looking at yourself in your camera. Okay, so now what are we saying? If an adult is selected at random, so it's anybody, we're not narrowing down our sample space, we're looking at the whole thing, find the probability that the person suffers from depression. So which one of those leaves, or which one of those endpoints are people who are depressed? This one or that one? Are we using an or given that? We're asking, what's the probability that they suffer from depression?
And both. I don't know.
Well, thanks for trying. First of all, it'd be helpful to actually calculate those probabilities. We know that we're interested in those depressed people, so let's calculate that branch. So 0.514 times 0.134. So that's 0.0689. And then this branch down here was 0.486 times 0.094. That's 0.045684. So what we have here is that there's a almost 7% chance that if you randomly choose somebody, they'll be a depressed woman. And then there's a 5% chance that if you just randomly choose someone, they'll be a depressed man. So then together, what's your overall probability of just, choosing somebody at random and they'd be depressed? What would we do with these two numbers? Yeah, we'd add them together. So you add them together, and you get, 11%. So 0.11456. And we added them together. Now, why did we add? Because we're essentially using the word or, meaning they could be a depressed man or a depressed woman. Either of those events was acceptable for the question you were asking.
I didn't verbally say it right, but that's what I meant.
Okay, wonderful, Simone. That's great. You had your gut instinct. All right. Just have a couple more. All right, yep. Just a couple more from chapter 7. We're going to do number 90 next. Number 90. College students were given 3 choices of pizza and asked to choose one. The following table shows the result. So, always a good idea to first look at the table and make sure you understand what's happening in there. How many freshmen responded to the survey? 46? And how many sophomores responded? 45? And how many juniors responded?
46.
About 56. Yeah. How many seniors responded?
50.
Yeah, and then we already know the totals for cheese, meat, and veggie, which was almost identical. But now the total all the way down would be 180 plus 17, 197? Is that the correct total? Is that what I get if I added these up? Because the row totals should add up to the same as the column total should add up. And
Yes, that's correct.
yes, that's correct. Yeah, so we have a total number of students who were asked, which was 197. And then we also know our total freshman, total sophomore, etc. We also know the total number of people who like cheese, meat, and veggie. So, a student is selected at random. Find the probability that the student's favorite topping is meat, given that the student is a junior. So what does the phrase given that mean we have to do? Yeah, reduce our sample space. So our sample space is now just juniors. So when we do our probability, our sample space becomes just juniors, which is 56 of them. And then only looking at the juniors, you might want to draw a circle around that column. Only looking at the juniors, what's the probability that the favorite topping is meat? Yeah, just the 15. It's 15 out of 56. So again, that's a good and powerful use of the phrase given that in order to reduce your sample space. And the other one that I wanted to do with us, this is it, folks. That's the last one from chapter 7 is 91. People in the survey were given 3 choices of soft drinks and asked to choose one favorite. So cola, which is Pepsi, Coke, or RC, root beer, lemon lime. What is a lemon lime drink? Like Sprite? Does that mean Sprite and 7-Up?
Yeah.
Is 7-Up lemon lime?
Yeah, it is.
Okay. And then totals. Okay, so you've got people under 21, people between 21 and 40, and then over 40. Wow, those are some drastic age chunks, aren't they? You got like maybe teenagers and children, and then, you know, people trying to figure out their life, old people. No, I'm just joking. I'm just joking. I'm allowed to make that joke. All right. So it probably wouldn't hurt. Well, let's just read the question. One of the participants is selected at random. Find the probability that the person is over 40 and prefers cola. Okay. There's good use of the word and. And refers to the intersection symbol or refers to the union symbol. Because remember, and means both, and union means either. And furthermore, what are these symbols called again? This is called
Intersection.
the other one.
U.
U for union.
Oh, yeah.
And the upside down is intersection. Exactly right. So that the upside down one is intersection. And so I just want you to see how language works out, that in this case, the word and should bring all these things up in your mind. And means to multiply, and means intersection, and means both. So when we look at this, and it says, find the probability that the person is over 40, so that means here, and they prefer cola, so that means here. And so what are we looking at? If someone is over 40 and they prefer cola, how many people were that? How many people was that? 20. Just the 20. Well, we are saying one of the participants is selected at random. There is no given that. And since they didn't say given that, what's my sample space? Everything. The sample space is always everything unless they say given that. So we need to add up all of our totals and see how many people there actually were. So in this case, it was 85 plus 85 plus 85. Because I can just look at the row totals, add those together, and that's 255. And so we're merely looking at the probability of 20 out of 255. Probability is 20 out of 255. So again, notice that because they never use the word given then, we just automatically go with the entire sample space. And because they said and, we were looking at the intersection of that row and that column. Okay.
That was fun.
Oh, good. Wait, you mean watching basketball or doing the problems?
It was a split.
Oh, a split? Yeah. Okay. Okay, now what I did, folks, is I already wrote up all the solutions for chapter 7. I did all the problems. So even though we just skipped a whole bunch, I did them all, and I just scanned it today, and I'll post it. So you can look at the solutions from what we just did, as well as looking at the solutions to any of the other problems that we skipped, and you'll be able to look at all that.
Did you already go? I think so.
Did I already give you the practice test?
Remember? No, he has it.
Let's see here.
You want one?
Sure do.
Well, gee whiz, I brought chapter 9, but I did not bring the practice test. I'm sorry, Louise. But no, I did not give it to you yet. Let me look. No, I did not. Okay, but since we are about to switch over to do chapter 8, let me see here. Maybe now would be an appropriate time for us to all take a nap. Chapter 8, we're going to be looking at counting permutations and combinations. Do you remember those phrases?
Yeah.
Permutations and combinations? Really? Why are you all so affirmative about that? Was it a previous business class or a previous?
We did it 213. Did all this.
Really?
No, or was it one?
I feel like I tried it.
I don't think you did it in 150 or 213.
Or was it 140? We took.
I bet you did it in 140.
That's
Yeah, I bet they do things like that in 140. There you go.
You're my teacher for 140.
No, I was not. I was a teacher for 150. Douglas Williams was a teacher for 140.
I didn't take 140, so probably.
Well, then I certainly wasn't a teacher for 140 if you didn't take 140. You're funny. Okay, so everyone, do you have your chapter 8 packet since you grabbed one?
He goes high school, I think it is.
Oh, okay. All right, yeah, probably was high school. Well, in any case, let's take a break. I think that's a good idea. I realize it's not the normal break time, but it's 3:09. Let's come back at 3:19. Everybody can go get a drink.
I think that's what I was really confused with, because we're about to learn it. Because I keep telling you, and it's supposed to be somewhere in this, and I'm like,
No, it's not. This thing is
Ooh.
no, it's not. Like,
No, I didn't realize that's how I said it.
No, it's not.
Oh man, that's funny.
I knew it.
See, you made me laugh so much. And you said,
No, it's not.
Because you did.
oh, okay. Because I did, she says. Simone, it must be true then.
See,
The minute you got it, I'm like, oh. No, it, the lid, it was like, yeah. What? Isn't that weird? Like, I really want like lemonade. I'm like, oh.
I'm gonna go down to the cafeteria and get a drink. That's what I want.
Oh,
Something tasty. You're gonna try. Oh no.
so funny.
Luis doesn't need an excuse to laugh. He's just breathing, taking in life.
Did I send you the stuff?
Yeah. That's too much reading.
It is. I took the pictures previous, of like when the chapter started, and then so
She gets mad because I misspelled some stuff. I'm like, you give us like 5 minutes to write like 10 sentences.
she always be like, "On mine's you did like 30 sentences," and I was like, "Don't give me this shitty homework."
I know, that's what I do.
She's still giving me 4 points.
I know. She's like, just be careful.
Oh,
I'm like,
see.
no wonder only like 8 people signed up.
It's dead in there. I'm just like, damn. Do we need this class or not? I'm trying to convince her to make the finals online so I can actually like, do good on it. Our teacher, I don't know her name, but our psych PBS teacher, and I don't know.
I don't know, it's true, I don't know her
What
name.
GPS were you
205.
Um,
Since 205 is business.
legal, ethical, and
Oh,
I
wait,
got shit
wait,
that has that shit.
I have an A.
yeah,
I have an A.
Peterson.
Something like that.
Ooh. You know what?
But she said this is her first time doing that, like hybrid. That she usually does it all
Oh, that's a
online.
hybrid? No, it's a full.
We turned everything, mostly everything on.
Oh, okay, but
We got a
it's a
test
full.
today too.
Yeah,
What you get?
like literally on every test, and I don't get how the fuck. Every test I get is like 21 or 25. Maybe like essay, I really don't
Yeah, watch the movie. So.
Oh, yeah. Hey, Diego, when we took the business ethics, it was Peterson, right?
Something like that.
You guys still have your essay?
I was gonna ask, but I was like, I won't. So I want to send that shit.
It's okay, I can switch some stuff up.
Right. What movie did you watch?
I watched,
Wall Street?
No.
I see that.
Saturday. I'm doing Dallas.
I actually watched the movie. I don't know what translation is. Yeah, I think it was.
I got the fire escape from Amazon. I was like,
I hadn't watched it. I was watching it on TV and the scene comes out with the snorted coke and put his ass and shit. I was like,
saying like I hate like most of those movies are like are shadows to watch. I hate movies. Did you get me now?
Yeah.
Did you get your mom her gift yet or not?
Oh, no.
Oh, okay.
No. Her birthday's coming up. Next month. Well, not March, April.
Oh, it's this far.
She's getting a Louis Vuitton bag. It's worth it.
Yeah.
what?
Listen, my birthday's September 25th. You can give me a bat.
I got her two already.
Oh,
She ripped one of one. I was like, how the hell do you rip a Louis Vuitton?
right. No, does she have like younger kids?
She's my nephew. She gives it to my nephew. It's small and she's the one big one.
Mhm.
He was swinging it around the store and it flew.
That's I can't give kids stuff. Oh, that sounds just like my niece.
But it wasn't even broken. Like the strap, like to hold the strap, it was just that little part that broke off. It's just like I need a new one. Like what?
Okay, well, that's why I never my nieces and my makeup. And like all my highlight is on her fingers, and I'm like, bitch, I need to know it. But anyways, I was thinking on myself.
I got my sister a Zapper bag. I got her the Beyond makeup is expensive.
Yeah, oh yeah.
It's Fenty or something.
Yeah, Fenty is yeah, it's up there.
I'm like $30 for a lipstick. This really worth it. Yeah, I went to Sephora. I tried some Emily. I think it was 12 hours water resistant.
Oh, it's that thing. You put on lipstick.
I think. And then I like try to wipe it, and then like it smeared more. Like I got all over my hand. You recorded it. So that's all.
trying to do one to every other time. So much shit. Was the country loud? Or not really? We just have like good ears. When I was trying to eat and
Yeah, I was like, where are they?
That's enough.
You didn't give a fuck earlier, so I thought you gave a fuck more.
Because I actually had to go to the bathroom last time though. I was like, since I'm out, might as well.
All right, folks, it's 3:19. Let's do it. So, this section is on slightly more advanced techniques for counting things. Like we've talked about a sample space, and a sample space is a total of all the things that could happen. Well, we use permutations and combinations to calculate that total. What are all the different ways that something could happen? Now, to be fair, we've already seen two ways to calculate all the different ways something can happen. One way we can calculate it is the fundamental counting principle, which allows us to use buckets and then say to multiply those buckets together, and we get a total. The other thing we've seen, well, it's still the fundamental counting principle, but like heads and tails, we saw that if you wanted to flip a coin 5 times in a row, how many ways could that happen? Well, there's 2 ways, heads or tails, 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 2 ways, heads or tails. And we get 2 to the 1, 2, 3, 4, 5, 2 to the 5th. So sometimes when you use the fundamental counting principle, it's a different number in each bucket, but sometimes it's the exact same number in the bucket. And it ends up just being an exponent on a base number. So that's the fundamental counting principle. But there are more situations that go beyond just the fundamental counting principle, and that's permutations and combinations. Okay, I really think I'm going to take some of stuff. What does everyone think? I think we can do it this time. Go for it. Okay, so let's look at just a couple simple warm-up questions. Okay, these are some warm-up questions. So, some basic example of factorial, permutations, and combinations. And I'm going to say, gosh, 5 people is so many people. But we'll stick with it. So given 5 people, the first question is, how many ways could they win a race? Okay, so you've got 5 people. They all take off from the starting line at the same time. And assuming that nobody ties with anybody else, how could you put them in order in terms of the first place, second, third, fourth, fifth place? So what do you think? How many different ways could you have people win? Well, let's look. let's consider the fundamental counting principle, which it is called the fundamental counting principle because it is the basis of even permutations and combinations. So how many different choices do we have for someone coming in first place? 5. Yeah, there's 5 different people who could come in first place. But now that person has already won first place. So now how many different choices are there for the person coming in second place?
We go 4,
Yeah, 4.
3, 2.
Yeah, you kind of see what's happening there, right? So this idea of saying how many different people could win, how many people are left, how many people are left, how many people are left, and so on, this naturally leads rise to the notation called factorial notation, which is an exclamation point, 5 factorial. So 5 factorial means 5 times 4 times 3 times 2 times 1, which if you actually multiply that out, you get 120. What's that, Luis?
Sure, we didn't do it in 150. Remember.
I mean, maybe we might have introduced that notation for some reason. Yeah, maybe. Yeah. Okay, so it's still the fundamental counting principle, and you'll notice that in the fundamental counting principle, sometimes each number could be wildly different. The numbers could all be the same, or the numbers could be counting down, like 5, 4, 3, 2, 1, like what we just saw. And when it does count down, that's a really nice thing, and we call it factorial. So I'm going to go ahead and write factorial. And factorial is given by n factorial. Okay? Just something to note real quick. 5 factorial, pretty easy to do. You start at 5 and you count down. 3 factorial, pretty easy to do. You just start at 3 and then count down. 1 factorial, still pretty easy to do. You start at 1 and you count down 1, and it's just 1. But there's a definition that we all need to know, and that is what is 0 factorial. Well, 0 factorial doesn't even make any sense. Because if you're already starting at 0, how do you count down to 1? You're already at 0. So by definition, mathematicians, by definition and by convention, we all agree that 0 factorial is just equal to 1. Okay, so that's the first question. Permutation. How many ways could 3 of the 5 people just take gold, silver, and bronze? So now we're only interested in who's coming in first, second, and third place. We don't care about 4th and 5th place, right? They just lost. Whereas 1st, 2nd, and 3rd place. So now let's consider 1st, 2nd, and 3rd place. So how many ways could someone come in first, then 2nd, then 3rd? So how many ways do we have for someone to come in first? 5 still. There's 5 people to choose. Then one of them is first place, and then how many people could come in second? 4. And then how many people? Yeah. So it's just 5 times 4 times 3. Now you notice we didn't count all the way down. You're just multiplying 5 times 4 times 3. We can all multiply that in our head. And that's trivial. 5 times 4 is 20 times 3 is 60. But more importantly, what I want you to notice is 5, 4, 3 is almost counting all the way down. So I want you to notice there's a trick here. If I had 5, 4, 3, I'm like, oh man, I really wish I could finish writing 2, 1. Because instead of writing 5, 4, 3, I could write 5 factorial. But the problem is I don't have a 2, 1. Well, watch this. There's a very clever trick. I would like to go ahead and write 2, 1. So if I write it there, all I have to do is write it down below as well. And then those cancel out. And this is the same as just 5, 4, 3. So multiplying 5, 4, 3 is the same as multiplying 5, 4, 3, 2, 1 all over 2, 1. Because then the 2's and the 1's cancel. And now what I can say about this expression, 5, 4, 3 is actually 5 factorial over 2 factorial. And that's just clever. It's clever. Because it's so much easier to just go ahead and say 5 factorial, 2 factorial, than to write out some partial list of numbers. So like for instance, let's say I wanted to multiply 10 times 9 times 8 times 7 times 6. Nobody wants to write that. So what could we do instead? I could very cleverly go ahead and finish the list on top. 5, 4, 3, 2, 1. And then what do I put on bottom? 5, 4, 3, 2, 1. And now, instead of writing 10, 9, 8, 7, 6, I can just write 10 factorial over 5 factorial. And that's just a savings. It's a convenience. It's something nice that we can do. So in any case, that's permutation. What we notice about permutation, what makes permutation permutation, is that order matters. So put a big star and write that down. Order matters. We know order matters in this case because of gold, silver, and bronze. Order matters a whole lot to whether or not you're getting a gold medal or a silver medal or a bronze medal. It matters to you, and therefore order matters. You want to come in first, not third. Okay, so that's a permutation, order matters. Now a combination, in that case, order does not matter. That's the key difference between a combination and a permutation. Order does not matter. How many ways could 3 out of 5 people join a committee? So when you join a committee, no one is special. In a committee, there's no president, there's no vice president, there's no secretary. You're just 3 people on a committee. And you're completely equal, and you participate equally. So whereas in a permutation, the order mattered because you want to be gold, not silver. In a committee, you're just a committee member. So now let's try to answer that question. So how many ways could 3 of the 5 people join a committee? First of all, let's take a look up here at one of the possibilities for 3 of 5 people taking gold, silver, and bronze. Let's just consider, let's see here, Abe, Betty, and Carl. Okay, those are 3 of the people who ran the race, and I'm just going to call them ABC. Okay? So when we look at Abe, Betty, and Carl up here, does it matter in terms of gold, silver, and bronze if I say ABC or ACB or BAC or BCA or CAB or CBA? Do those all represent different placements of gold, silver, and bronze? Yeah, like here, Abe got gold and Carl got bronze. Whereas here, Carl got gold and Abe got bronze. So these all represent different orderings, don't they? And yet, do these each represent the same committee? I mean, all of those committees just represent a committee with Abe, Betty, and Carl. Okay, and there's no order in a committee. It's just 3 people serving on a committee. So what we notice is that for every single combination of people up here, there's actually, in this case, 6 different ways that you could write out those names, which are equivalent in terms of a committee. So even though that is 6 different placements for these people in terms of winning an award, all of those represent the same committee. And that's because there are, how many ways can you rearrange 3 letters? You could either have 3 choices for the first one, and then 2 choices for the second one, 1 choice for the next one. That's 3 factorial ways that you can permute 3 objects. And we want to divide that out of the 60 different ways people could take an award. So what we're doing here is then, how many ways can you make a committee of 3 people out of 5? Well, there are 60 different ways you could list 3 people. But a whole bunch of those are duplicates, right? A whole bunch of them are duplicates. And so the answer to how many committees you can make is a lot less than 60. Because so many of those lists up here are going to be the same committee. And specifically, for every possible group of 3 people, there are 6 of them, 6 different permutations that are listed up here. So the answer would be you take the 60 from above and divide it by the 6 different repetitions or the 6 different duplicate answers, and you would say there's actually only 10 committees. So we're dividing out all the duplicates. What's interesting to notice here then is that this was really 60 over 3 factorial, which is really this number divided by 3 factorial. So the actual combination answer is out of 5 people, 2 of them don't matter and 3 of them do matter. And that would be your formula for combination. So I'm just kind of covering some basic conceptual ideas here, but I wanted to kind of preview the fact that these formulas would be listed out in various ways, all in terms of the factorial. So factorial is just how do you permute that many objects? A permutation is a clever way of rewriting a partial list. And then a combination is a permutation where you divide out all the duplicate entries because order doesn't matter. Okay, one last idea is Pascal's triangle. I bet you've all seen Pascal's triangle before in the past. And everybody draw Pascal's triangle with me. You have space there, right? You have space to write it down? Yeah, you do. So to draw Pascal's triangle, you start with the number 1. And then down below it, you make a 1 to the left and a 1 to the right. So far, does it look like a triangle? Christmas tree. Yeah, a little Christmas tree. Now what you do is you always proceed to draw another 1 to the left and another 1 to the right. But anytime you see two numbers next to each other, you add them together and write the result in the middle. So 1 plus 1 is 2. So anytime you see two numbers together, you're going to write their sum below in the middle. So watch the next row. Again, I put a 1 to the left and I put a 1 to the right. And now, underneath 1 plus 2, I write a 3. And underneath 2 plus 1, I write a 3. And this is how you make Pascal's triangle. To be fair, Pascal's triangle was around a lot longer, was around before Pascal. He was a mathematician in like the 1700s in Europe. The Chinese were using this long before then. Probably other mathematicians. This is probably just us who call this Pascal's triangle. But let's do it again. A 1 to the left, a 1 to the right. And then underneath every pair of numbers, you write the sum. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. What do you notice about Pascal's triangle? That it's, very good, it's a bunch of numbers. It's symmetric. What you see on the left appears on the right. It's symmetric. Let's do one more row. 1 on the left, 1 on the right. So 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. And you can see that the list is symmetric. It goes 1, 5, 10, 10, 5, 1. Now I just want you to see something real quick. Pascal's triangle is important because it is the answer to any combination question. So if you have a combination question, you can look up the answer in Pascal's triangle. So for instance, out of 5 people, choose 3. Everybody watch this carefully. You go to the row that has a 5 in it, and ignoring the 1 out front, you would say out of 5 people, choose 1, 2, 3 of them. And the answer is 10, which is the answer we got. So you can use Pascal's triangle to say, how many ways can 3 out of 5 people make a committee? Or out of 5 people, choose 3 of them to make a committee with no order? You would go to the 5th row, and then look for the 1, 2, 3rd actual number, not the 1 in front. You start with the actual numbers, and that's how many committees you can make. Okay, had you seen Pascal's triangle before? Cheryl, had you seen it before? Pascal's triangle? No, Josue? Luis? Simon? Yeah? Diego?
I don't think so.
Oh, sweet. Baza? Are you there? No? I'm so excited to introduce you to Pascal's triangle. Well, it's super fun, and we'll use it as we proceed through our list. So, that was a little overview. That was to introduce you to some concepts, and we will proceed to do more and more. So, whoops. Oh, no. No, in fact, I don't know if you guys noticed this, but on the syllabus, today's class goes until 5:30.
Pay extra.
No, it's free. That's free. Simone, I knew you'd be especially excited about that.
I'm like the quietest one. Like.
All right, so first of all, folks, I think you're all going to find this extraordinarily much better than chapter 7. This is all pretty straightforward. So evaluate the factorial, 7 factorial. First of all, you can write it down, 7, 6, 5, 4, 3, 2, 1, and you can type it in your calculator, 7 times 6 times 5 times 4 times 3 times 2 times 1, but unfortunately there's a button. So everybody, open up your calculator, open it up, take out the batteries, eat them. No, that's silly. Take out your calculator, type the number 7, and then you need to go to my favorite button, the math button. And then you go all the way to the right where it says PRB. Now you can either go to the right or you can push left and you actually show up over there like in Pac-Man. Now you go to the left and then you come back on the right hand side. So under PRB, if you scroll down, everybody see the exclamation point? Did you find it? Everybody? So just hit enter and now your screen says 7 exclamation point. So everybody, I want to make sure that you found it. You found it? You find it? Yeah, good. You found it, Diego? Oh, I'm so sorry about that. Adon, you found it? Yeah. Simone, you found it? What's right? You sure? Luis? All right, so what's the answer? 5,040. There are 5,040 ways that I could take 7 of you. So 1, 2, 3, 4, 5, 6, 7. If I just took 7 of you, there would be 5,000 ways to put you in line. That's crazy. Okay, now everyone take a look. This is a special notation right here. This is a permutation. And what we're saying is, we'll write it out in English first. Out of 10 people, permute 6 of them. So what does that mean? That means I have 10 people to choose from, which, by the way, there are 10 of us in this room. So out of the 10 of us, I'm just going to have 6 of us go line up against the wall, and I'm going to count how many ways I can put them in order. Okay, so you'll notice that there's 2 actions of choice. First, which 6 of us do I choose? So that's one choice right there. I got to grab 6 of us, put us up against the wall. And then once I put you up against the wall, I need to choose what order to put you in. It's overwhelming. Honestly, it's overwhelming to think about all the different ways that could happen. Which 6 of you do I choose? And then what order do I put you in? So anybody, what do you think the answer is? How many different ways could you take 6 out of 10 people and then put them in order? Thousands of ways?
Yeah.
Millions of ways? So here's how it works. There's a formula, and I want you to know that this program uses P of 10 comma 6, but your calculator uses the notation little 10, capital P, little 6. I want you to see that on our calculator, because you need to type in the number 10, and then you go get the command. So you go 10, then you go math, then you go PRB, then you scroll down to NPR. You see that where it says NPR? Yeah, it's number 2. It's option number 2, NPR. So now you hit enter, and so far you have 10 NPR 6. So everyone, now your calculator says 10 NPR 6. And that's the same as this notation I just wrote down here. Okay, so out of n people, permute 6 of them. And hit enter, what did you get?
151,200.
Yeah. Oh my goodness.
We have to count that.
Yeah, it'd be terrible. Now, it's wonderful that your calculator can do that for you. Like, literally, the calculator just told you how many different ways you can choose 6 people out of 10 and then line them up against the wall and put them in different orders. So that's a lot of different possibilities. But I also need you to know the formula. Yeah. 10 NPR 6. Yeah, hit 6 and then hit enter. There you go. Okay, so what's the real formula? Everybody, let's write it down. The actual formula, P of n comma r, where again, out of n people, permute r of them. The actual formula then, NPR, I'm showing it in both notations. The formula is n factorial over n minus r factorial. That's the formula. And I think I'll leave that up on the board for us. So NPR is n factorial over n minus r factorial. Now let's all look at this and really understand it. First of all, out of how many people? 10. And then choose 6 of them, or permute 6 of them. So that'd be 10 minus 6. Right? So we're actually doing this problem now. We're going to see where that came from. So that's really 10 factorial over 4 factorial. And then if you just did that in your calculator, you should get the same answer. You'd be able to go 10, math, PRB, exclamation point, divided by 4, math, PRB, exclamation point. I divide that, and I still get 151,200. However, also there. Everyone keep writing. Actually, write out now the top. We're just going to do this once. It'll only hurt a little. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Now write out the denominator, 4 factorial, 4, 3, 2, 1. And what do you get to do? Cancel out those 4, 3, 2, 1s. Now, I want you to look real closely at what those numbers are. Because the original question we could have calculated using buckets, using our bucket notation. If you want out of 10 people to permute 6 of them, you would have said, who do I choose first, second, third, fourth, fifth, and sixth? And how many choices did I have for my first person to put up against the wall? 2. And then after I put that person against the wall, how many choices do I have for the second person? And that's exactly what this computation gives us. That's exactly what the formula is. So if I had just used buckets to solve this problem, which you can, I would have just said, well, so far that's my answer, but I'll go ahead and put 4, 3, 2, 1 next to it, 4, 3, 2, 1 next to it, so that I can write it out as 10 factorial, 4 factorial, And then I would have noticed that 4 is actually 10 minus 6, and hence that's the formula. Okay. So I just wanted to close the loop on that so you see where the formula comes from. The formula is really just buckets, and it's writing in bucket information in a convenient way. Okay, so let's try the formula a couple times. Everybody write down the formula again. NPR is n factorial over n minus r factorial. I go ahead and do this one. It says, how do you permute? Out of 7 people, permute none of them. That's a silly question. Out of 7 people, how many ways can I choose none of them, have them line up against the wall, and mix them around? How many ways can that happen? If I choose none of you and have you come up against the wall and put you in order, how many ways can I do that? Yeah, exactly, 1 way. I say, everybody stay where you are. There, I just did it. I chose none of you, put a view against the wall. There's 1 way to do it, that is, you do nothing. So let's look at what our numbers say then. It'd be 7 factorial over 7 minus 0 factorial. And that's 7 factorial over 7 factorial, which is 1. So there's 1 way to choose nobody and put them in order. Equally interesting, look at the next one. How do you permute out of 6 people? Permute all 6 of them. So out of 6 people, permute all 6 of them. So now this would be 6p6, which is 6 factorial over 6 minus 6 factorial, which is really 6 factorial over 0 factorial. What's 0 factorial? 1. So that's really just 6 factorial, which reduces to the general factorial notation. General factorial notation is the case where you permute all of them. You're just taking everybody and you're permuting them. Well, that's permutation. And remember, you have n people, you take r of them, and you want to mix them all up. And you want to count how many ways you can do that. Any questions so far? Any feelings so far? Did you hear the news? Class goes until 8 o'clock tonight. All right. Next set of questions. Now, here are a couple word problems to apply this. To apply any of the concepts that we've seen so far. So, suppose there are 8 roads connecting town A to B, and 7 roads connecting B to C. How many ways can a person travel from A to C through B? So, like, for instance, if I'm starting from A and I go to B, how many ways are there to do that? How many ways are there to go from A to B? There are 8 roads from A to B. So how many ways are there to go from A to B? 8. There are 8 ways to do that. And then how many ways can we go from B to C? 7. And so overall, the total number of ways is just 56. This is just the buckets. This is just, well, I call it the buckets. It's the fundamental counting principle. You have 8 ways to do the first thing, 7 ways to do the second thing, and so you multiply. That's what the fundamental counting principle states. It states that if you have lots of options for one action, lots of options for another action, you multiply, and that gives you the total number of ways to do your action. Next one, how many 3-digit numbers can be formed using the digits 0, 1, 2, 3, 4, 5, 6? And it says if repetitions are not allowed. So first of all, everybody, we're making a 3-digit number, so build 3 buckets. And how many choices do you have for the first number?
6. Wait, 7.
Yeah, 7. Now notice it says repetitions are not allowed. So the number that I just used, I cannot use again. So how many choices do I have for the next digit? And how many for the next? So that's how many 3-digit numbers can be formed. Now, you can just take that and multiply. 5 times 6 is 30, times 7 is 210.
So smart.
Why, because I did that? Oh, I did it. 5 times 6 is 30, and 3 times 7 is 21. That's pretty simple. But thanks enough. That'll boost me through the rest of the day. Okay, license plates. These license plates are made using 2 letters, so that's a letter and a letter, followed by 2 digits, so that's a number and a number. How many plates can be made if repetitions of letters and digits are allowed? So how many choices of a letter do you have?
26.
And still, how many choices of a letter do you have? And then how many numbers do you have to choose from? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, because there's a 0 there as well. So you've got 1 through 9, and then 0. So that's 10. And still 10 choices for a number. And you multiply it all together, and that's how many license plates there are. How many license plates is that?
67,600.
Yeah, 67,600. Is that enough license plates for the state of Arizona? No. We have a lot more people than that. How many people live in Arizona? Really, 8 million? Yeah. So how many letters and numbers do you actually have on your license plate? Is it 3 and 3? Do you know?
Yeah.
I think mine's 3 and 3. So I have 3 letters and then 3 numbers. So that would be 26 times itself 3 times, times 10 times itself 3 times. And I wonder, 26 to the third times 1,000. That's 17,576,000 people. So is that enough license plate possibilities?
Yeah.
Yeah, because we have 8 million. So there's 17 million possible license plates. However, not all of those license plates are valid because some of them spell bad words. And we don't let people use those as license plates, right?
Right.
So that's just the maximum number. But that should be plenty, right? Especially because, some people, license plate, I don't know.
Or just numbers.
Yeah, some people just have numbers and some people have personalized license plates. But the key is that 3 and 3 is more than enough. Okay, moving along. How many letters are in the alphabet? Yeah. Yeah, that's 26 letters in the English alphabet anyway. I realize every different language might have a different alphabet. But they were talking about the English one. Does that answer your question, bud?
Yeah.
Oh, Basil, what's your question?
No, I'm just telling you some, no, 2 years ago it was 7 million.
The equation?
Yeah, probably a million more.
Well, listen, it's not really an equation. We're just saying that a license plate has 2 letters and 2 numbers. The digits is a number. So I've got my letter, a number, and a number. And how many choices do you have for a letter? 26. How many choices do you have for a letter? 26. How many choices do you have for a number? It's 10 because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. And likewise there. And then you just multiply all those choices together. Okay. Let's keep going, folks. Number 8. This one's very interesting. How many distinguishable permutations are possible? So first of all, remember, permutation, to permute means to rearrange. To permute means to rearrange. So permutation means to rearrange. So I just want you to know that if I went ahead and rearranged these letters, I could spell sticker. Right? Did I spell that? S-T-I-I-C-C-R? That is a permutation of the word critics. Is it a word? No, it's not a word. I don't even know that I can make another word out of the word critics. But that is nevertheless one permutation out of, so let's look, how many permutations are there? 1, 2, or how many letters? 1, 2, 3, 4, 5, 6, 7. So we already saw that answer. 7 factorial was 5,040. So there are 5,040 ways to permute all those letters and create different combinations or different permutations of letters. However, they're saying how many distinguishable permutations are there? So I want you to notice now, what if I take this permutation and switch the C's? S-T-I-I-C-C-R. I promise to you, I switched those 2 C's. But is the result the same? Yeah. So these are not distinguishable permutations because I can't tell the difference between them. Whereas if I switch the I and the C, then S-T-I-C-I-C-R, that is a distinguishable permutation. I can tell the difference between it and another one. So basically what we're saying is that as we look through all 5,040 permutations of these letters, some of them will be the identical thing. because I've switched the two that are the same. And so the rule here is that you start by looking at all 7 factorial ways of permuting. And then again, you divide out the duplicates. And so I've got duplicate i's and I've got duplicate c's. And since, how many different ways can I permute 2 i's? 2. Yeah, that'd be 2 factorial, which is just 2 times 1. And how many ways can I permute 2 c's? Another 2 factorial. So what you do is you divide out the duplicate i's and you divide out the duplicate c's. And that will take your 5,040, but then reduce it and divide out the 2 times 2, which is 4. That'll reduce my list all the way down to 5,040 divided by 4, 1260. So there's actually only 1,260 distinguishable permutations of the word critic. Again, because for any given word, you could permute those letters. And actually, I'll even show it to you. Consider, there's actually 4 copies of the word sticker. Do you believe me that there's 4 copies?
Because it's 2 C's and 2 I's.
Yeah, because I could either, I have the I's and the C's the way they are, and then I could either switch the I's, or I can switch the C's, or I can switch the I's and the C's. So does everyone see that that's really, this word would be listed 4 times? And so that's 1, 2, 3, 4 copies. And what I divide by? 4, because I divided out the 4 copies that are duplicates. Okay, so try that again. The word look. How many total permutations are there? 4 factorial. And how many letters do we have duplicates of? Just the O's, so we divide out the 2 factorial. So 4 factorial is 4, 3, 24. 2 factorial is 2, and so there's only 12 distinguishable words. Which is pretty funny to think about. Gosh, 12 distinguishable permutations of the word look. Hola, hello, Google. Anyway, I'm not going to list all 12, but apparently there's 12. Okay. All right, super. Just a couple more problems to try with permutations, and then we'll do combinations. So again, permutations order matters. So let's take a look at some of these. Okay, given a group of students where G is the group, Alan, Brenda, Chad, Dorothy, and Eric, we will just represent them by A, B, C, D, and E. They count the different ways of choosing the following officers or representatives for student congress. So what are some traditional? Vice president, historian, etc. And they're saying, assume that no one can hold more than one office, so that makes sense. Nobody can be president and treasurer. And they want us to count all the ways these things can happen. So what are all the ways that the president, the secretary, and the treasurer, if the president must be a woman and the other 2 must be men? Okay. So, first of all, how many people total do we have? We got 5 people. And out of 5 people, how many of them do we want to permute? President, secretary, treasurer, just 3. So already that's the answer. 5P3. It's just saying out of 5 people, choose 3 of them and give them a position of president, secretary, or treasurer. So even if you just wrote that, you already have the right answer. Because it says out of 5 people, permute 3 of them. Oh, I'm so sorry. There's more. Wasn't it? There's more to this problem. It's not just choosing. They're telling us the president has to be a woman, and then the other 2 have to be men. So I take it back. I need to finish reading the question. There's more to it. If all you wanted to do was choose 3 people to be those offices, it would have just been 5P3. But they're saying the president has to be a woman, and the other 2 have to be men. So let's look at it. What do you think we would do? I solved all of these problems using buckets, fundamental accounting principle. So let's consider, we've got a president,
We've got a secretary, we've got a treasurer. So how many choices do we have for president? Since the president must be a woman, how many of those were women? Theoretically, Brenda and Dorothy. These days, I have no idea. Alan could be a woman, Chad could be a woman, Eric could be a woman, I don't know. Okay, so, well, I mean, yeah, right? So, I mean, we're assuming traditional gender norms for those words. Because they didn't tell us, right?
Gender specified.
Yeah. So, but for president, then there's two choices. I'm honestly trying to be respectful for the fact that you never know what somebody's name is going to be. You have no idea. But we're assuming, we're making some big assumptions. Okay, how many choices do we have for secretary, considering that they must be men? So how many men were there? In theory? Alan, Chad, Eric. So there are 3 choices for secretary.
What about Dorothy?
Right, exactly, you don't know. But now secretary, whoever you just chose, now there's only 2 men left to elect for treasurer. Okay, so then the answer is just 12. There are 12 different ways that you could assign roles to those 5 people following those rules. Next question, a treasurer and a secretary if the 2 must not be the same sex. Now this one's interesting. We want to elect a treasurer and a secretary, and they just can't be the same sex. So for instance, it could be that the first one is a man and the second one is a woman. But that's not the only way to do it. Or, what do? Or it could be that the treasurer and the secretary was a woman and a man. And so by using the word or, I'm going to add these 2 different possibilities. So first of all, for the treasurer to be a man, there were 3 men and 2 women. That's treasurer secretary. Or for the treasurer to be women, there'd be 2 women or 3 men. And so we add all that together, 3 times 2 is 6, 3 times 2 is 6, so that's really 6 plus 6, which is 12. There are 12 ways to make that happen. How's that? Okay, next. An order of award presentations has been devised for 7 people. So first of all, we have 7 people. Jeff, Karen, Lyle, Maria, Norm, Olivia, and Paul. Good old Norm. So we got 7 people, and how many ways can the 7 people be presented? So first of all 7 of them are getting awards. So how many different ways can you permute 7 people? 7. Yeah, just 7 factorial. And again, that answer is already correct. And maybe you already have it memorized. It's 5,040. And how many ways can the men be presented first and then the women? So again, making some assumptions here. So the first thing you want to do is present the men. So how many different ways can the men be presented? How many men are there? In theory. Jeff, Lyle, Norm, and Paul. Is Lyle not a male name? I don't know. Yeah. See, it really boils down. And why would they even include a word like Lyle? My goodness, but I'm assuming it's Jeff, Lyle, Norm, and Paul. So that's 4 guys. So how many ways can you permute 4 people? The 4 factorial. And then we present the women, and there are 3 women in theory, and you can present them in 3 factorial. That's 24 times 6, which is 144.
You know my middle name is Lionel.
Is it really?
No, it's not.
I knew you were lying. I knew you were, Simone. Because your middle name is Bill. Simoneville. All right. Everyone can cross out 14 and 15, and we're done with permutations. Now, you'll notice that in doing permutations, we did not strictly use the permutation formula. We have a permutation formula, but there are lots of ways to compute permutations, including just regular old bucket theory and factorials. So a factorial is a permutation. The permutation formula is a permutation, and even buckets can represent a permutation. So I'd say the biggest challenge for any given problem that you look at is figuring out how to set it up. And ultimately what you could do is you could try it multiple ways. You know, try multiple approaches and then look at the answer you get and see which one seems the most reasonable. But I can tell you that basically buckets are always the answer. Okay, wait, where are we now? I said just cross out 14 and 15? Okay, combinations. What?
You said the whole page. That too.
No, just 14 and 15. Don't mess with me, Simone.
Okay.
Okay, now give the combination formula. Did I not have that in the previous one? Give the permutation formula. Yes, I didn't.
You did.
Oh, I didn't. I just skipped right over it. Did we write it?
Yes.
Oh, we did. Okay, well, great. So give the combination formula. That's NCR, which is n factorial over n minus r factorial, which so far is the permutation formula. The only difference is that we put an additional r factorial in the bottom. So that's the combination formula. And what that means is, out of n people, group r of them. And let's remind ourselves, order does not matter. You're just putting them in a group. So a couple of classic words that make you think of something where order doesn't matter is a committee, or a club, or a society. It's just people. So we go ahead and take a look here at C of 12, 5. That's one way of writing this. But the way we'll write it is 12C5, because that's what's in our calculator. So go ahead and go find that option on your calculator and write it down.
The answer is 792.
You want us to believe it?
I would hope so.
Well, you've already messed with me a couple times, Simone.
I know.
But I'm glad you have. Okay, yep, 792. Now, before I just write down 792, I'm going to go ahead and do the formula. So it's really 12 factorial over 12 minus 5 factorial, 5 factorial, which is 12 factorial over 7 factorial, 5 factorial. And, you know, at that point, you could do all that computation by hand or on the calculator. But yeah, the answer is 792. Now, I want you to appreciate that that would not be the worst thing to do in the world by hand. And in fact, it would be lots of fun. Look at how fun it is to actually do something like this by hand. I'm promising you it's fun. So first you have to write 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, which most people don't think is fun. They think it's monotonous, so they don't even do it. But then 7 factorial. I'm not even going to write 7 factorial. You know what it would look like if I wrote 7, 6, 5, 4, 3, 2, 1, and what would I do? Cancel all out. Now I'm going to write 5 factorial. That I actually will write. 5, 4, 3, 2, 1. First of all, the 1 doesn't matter. Next, the 5 goes into 10 twice. The 3 goes into 9 3 times. 4 goes into 8 twice. And 2 goes into 2 once. So what's my denominator? Nothing. What's my numerator? 12 times 11 times 2 times 3. So that's just 2 times 3 is 6 times 11 is 66. So far I have 12 times 66. And you multiply it and you get 792. Wasn't that fun? Yeah, Mr. J, yeah, it was a ton of fun. Yeah, all right, well, there we go. Okay, now these next two are just showing what happens if you do the extreme. So this says, out of 6 people, put none of them in a group. You should all be able to tell me the answer. Yeah, there's only one way to do that. You just don't tell anyone to do it. So that answer is automatically 1. And then what about, out of 37 people, put all 37 of them in a group? How many ways can you do that? 1 still. Yeah, so it's really just interesting in the middle. Like you're only taking some of the people. Okay, now we're about to do something which maybe some of you will find interesting, and that is compute. Okay, now first of all, let's just all understand how to play poker. Raise your hand if you have never played poker. Okay, so here's how poker works. I'm going to take a deck of 52 cards, and I'm going to deal everybody 5 cards. So you get a 5-card hand. And so everybody has 5 cards, and we'll just pretend we're playing 5-card stud, which means you get 5 cards and then that's it. That's your hand. And then you're looking for things. So what would be valuable? It'd be valuable to have a pair. Like you had a pair of 7s. You're like, oh goody, I have a pair of 7s. The other cards are meaningless. They're nothing. They're just random cards that do nothing for you. You can have 2 pair. That'd be pretty cool. If you ended up with a hand where you had a pair of 2s and a pair of kings, and then the other card is just some random card, who cares? That's a better hand. So if you're playing poker against somebody, and you have 2 pairs and they have 1 pair, you just won. Okay, but there's more than just pairs. You can have 3 of a kind. And then if you get 3 of a kind, you're like really feeling lucky. You're like, oh great, I have 3 of a kind. That's a jack and a jack and a jack, and the other cards are nothing. Okay, so now 3 jacks beats, a 3 of a kind beats 2 pair. Okay, so then what can happen next? What would be even better than 3 of a kind? You could have I think next is a straight. A straight is cool. That means your numbers go in order. So it could be like 5, 6, 7, 8, 9. And you're like, yes, I have a straight. And if you have a straight, you just beat the person with 3 of a kind. And on and on. There's other things you can have, such as a full house, like the TV show. That would be a 3 of a kind. So I'm going to do a 9, a 9, a 9, and a pair. So like a 3 and 3. So that's full house. What else is there, poker players? Yeah, you can have a flush, first of all. A flush means that they're all the same suit. So like that could be, what's the easiest suit to draw? Club, spade, heart, diamond. They're not easy, any of them. So heart, 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 that's flush. Doesn't even matter what the cards are. They don't have to be in order. And you obviously wouldn't have any pairs because they're all the same suit. Okay, so that's a flush. And then you have a straight flush, which means that you have a flush and they're in order. Like, what are the odds? Like, whoa, not only do you have a flush, but they even go in order. And then the last one is a royal flush, meaning a royal straight flush. They're all the same suit, they're in order, and it goes 10, jack, queen, king, ace. That's the best card hand you could have. Now, why did I just say to you that the lower down you go beats the other ones? So like 2 pair beats a pair, a 3 of a kind beats 2 pair, and a straight beats 3 of a kind, and a full house beats a straight. Did somebody just come up with these arbitrarily? Like, I think full house beats straight. Yeah, that's how they say it. Why is it that it's in this order? Because the probability of getting a pair is pretty good. The probability of getting a pair is pretty good. Whereas the probability of getting a royal flush is very, very, very small. So these are actually listed in order of probability. So if you go online and look up rules of poker, the hands that beat other hands, they're strictly listed in terms of probability. So this is the lowest probability, and this is the highest probability. Okay? So everybody, let's start by calculating a couple simple things right up at the top of your page. So first of all, how many hands are there? So just total, how many different possible hands in poker could you get? If somebody just dealt you 5 cards, how many different combinations of 5 cards could you get? And keep in mind, order doesn't matter, because as soon as you have your cards, you can put them in whatever order you like. It doesn't matter what order you put them in your hand. You just have these 5 cards. So first of all, how many hands are there? Out of 52 cards, choose 5 of them. Okay, everybody write it down, we're practicing. And then on your calculator, go ahead and find it. Out of 52, choose 5 of them. And what do you get? 2,598,960. Notice what they said right up front. Of the 2,598,960 different 5-card hands from a deck of 52 playing cards, how many would contain the following? So we just confirmed that that is the total number of possible poker hands. So 2.5 million. If you play poker every day for your whole life, will you ever get the same hand dealt to you twice? Seems like you do sometimes, but the chances are no. Okay, now what if you just wanted a pair? Everybody watch how I do this. This is very important. I'm showing you how to calculate these things. What if you just wanted a pair? Okay, what that means is, let's just choose a number. How many different choices do you have for a number? Right? So first, you have 13 different choices to choose what is going to be your pair. So it's going to be an 8. And then you're saying you have 4 of those, first of all. And so you just want to choose 2 of them. So 4, choose 2. So I just chose which card I'll have a pair of. From that, I'm choosing 2 of the 4 that exist in the deck. And then I just have how many other cards to choose from. There's 52 total, but I just took a pair, but I have to remove all 4 because I don't want to get 3 of a kind or 4 of a kind. So now I only have 48 cards left. And out of those 48 cards that I have left, I want to choose 3 more. Actually, no, to be fair, that would be no good because if you just chose 3 cards out of 48, you could end up getting another pair or another 3 of a kind, or something fancy could happen. So we have to be even more careful in terms of choosing 3 more cards that aren't the same as the previous one. Darn, I chose not the best example. Boy, to get a pair but nothing else, what would that even mean? I now have 48 cards left. Well, maybe I'm not going to finish this problem right now. Because I was just trying to do an example anyway of showing how many different ways you can get a pair. So you choose your first one. Well, actually, what you want is the last 3 cards to be all different, right? Yeah, that's what you want. You want the last 3 cards to be different. And so, since you've already chosen one of the 13 cards as representatives, you only now have a choice of 12 different cards to choose from. No. Oh, what you could say is you have 48 cards left to choose from, but as soon as you choose one of them, you have to remove the other 3 of that same representative. So then you'd only have 44 left to choose from, and then whichever next number you choose, you take away all 4 of them, and then you'd only have 40 cards left to choose from. Okay, there we go, that's it. So then what is that total? 4 choose 2. So that's 13 times 6 times 48 times 44 times 40. So let's do that out. 13 times 6 times 48 times 44 times 40. That means that there are a total of 6,589,440,000. That's how many ways you can get a pair. Just a pair. And what was the... I did that wrong, didn't I? That has to be wrong. Because that's more than the total number of possible hands. Well, gosh darn it. Here I was just thinking I'd do a simple example of showing you how many ways there are to get a pair. And I botched the whole thing. You know what I think I'll do? Instead, just going to go ahead and get it up here so we can all look at it. What is the probability of each poker hand? There we go. Bam. So everyone take a look. Wait, I didn't mess it up. I had the wrong thing written down. That was good. Mornings. Oh, that's a 7-card poker. Frequency of 5-card poker. There we go. Oh, well, it's not the plus. Okay, well, everyone take a look. Looking from the bottom. The probability of getting absolutely nothing is 50%. Oh, well, that's a bummer. 50% of the time, you're going to get absolutely nothing. 42% of the time, you'll get a pair. To get 2 pair is only 4% of the time. To get 2 pair is only 4% of the time. To get 3 of a kind is only 2% of the time. To get a straight is only 0.4%. So less than 1 in 100 hands. To get a flush, it's only 0.19%. To get a full house is only 0.14%. Oh, 4 of a kind, which I didn't even mention, is only 0.02%. A straight flush is only 0.001%, and a royal flush is only 0.00015%. So, what's the most likely thing to happen when you're dealt 5 cards? Is to have nothing or a pair. And then the list goes on from there. So that's how the game of poker was designed. They created these different events that they thought were fun. They ranked them in terms of probability, and then lower probability hands beat higher probability hands. Okay, well now that we've just seen all that, we just totally botched my calculation of a pair. Let's do these. I got a little ahead of myself. So, how do we get all 4 2s? how many ways can that happen? We're not computing probabilities, we're just counting. We want all 4 twos. So first of all, out of the 4 twos that exist, we're choosing all 4 of them. And then, since we already have 4 cards and we just need 1 more card, out of the 48 cards that remain, we just need to choose 1 of them. And that's the computation for getting 4 twos. What we mean is you have 4 twos, and then the other card could be anything. So again, out of 4 twos, choose all 4 of them. And then, out of the 48 cards that remain, just choose 1 of them. And if you compute that on your calculator, you get 48. So there's 48 ways you could be dealt 4 twos. And you can start imagining them. You can get 2, 2, 2, 2, and then a king. And then you can get 2, 2, 2, 2, and then a queen. And so on and so forth. You have 48 different ways that you can get 4 twos and then some other card. Okay, how about all black cards? How many black cards are there in the deck? 26. So all we're saying here is that out of 26 cards, choose 5 of them. So out of 26 possible black cards, just choose 5 of them. And that turns out to be 65,780. Okay? Now, what if you wanted, how many ways can you dealt a hand with no face cards at all? So a face card is a jack, queen, king. So how many jacks, queens, and kings are there? Yeah, there's 4 of each. So 3 times 4 is 12, there's 12. So 52 minus 12 is 40 cards that are not face cards. So out of the 40 non-face cards, choose 5. So 40 choose 5, 658,000. So that's quite a few. Just imagine 658,000 out of 2,598,000. That's about 1 in 4. 1 in 4 hands. You won't have any face cards at all. Okay, what about all diamonds? How many diamonds are there? 13. So out of 13 possible cards, choose 5 of them. And 13 choose 5 is 1287. Should have started with these examples and built up to a pair. Okay, 2 black cards and 3 red cards. So how many black cards are there, first of all? Yeah, 26. So we're going to, out of 26 black cards, choose 2 of them. And then, out of the red cards, choose 3 of them. So out of 26 red cards, choose 3 of them. And you calculate both of those and multiply them together. So the first number is 325, and the next one is 2600, which gives us a total of 845,000. So just looking at that, what's more likely? To get 2 black, 3 red, or to get no face cards? Yeah, this one's a little more likely because it can happen in more ways. Okay. Well, there we go. Those are some card probabilities. I'll show everyone this so that I can finish the thought that I was doing earlier. So how do you compute how many ways you can get 1 pair? This one is pretty crazy. So to get a pair, first, you'd have to choose one of the, you'd have to choose, out of 13 possible numbers, choose one of them that you're going to create your pair with. And then out of those 4 possible instances of that card, choose just 2 of them. So now what you have to do is choose 3 more cards that are all separate. Yeah, you're going to choose 3 more cards that are all separate. So out of the 12 remaining types of cards, you choose 3 of them. And then for each of those 3 remaining numbers that you're choosing, you have to look at each set of 4 of them and say,
From the 4 of the first number, choose one of them. And from the 4 of the second number, choose one of them. Again, my writing is terrible. From the 4 of the last number, choose one of them. And boy, that is a terrible computation. So you're choosing one number out of 13 for your pair, and then out of the 4 available, you choose 2 of them. And then out of the 12 different numbers that are left, choose 3 separate numbers. And then for each of those separate numbers, you need to choose one of the 4 that exist for that number. And oh my goodness, that's the computation. And that makes sense now that I see it. But it's pretty brutal to do it. I'm not asking anyone to do that. In any case, folks, you can notice on the website here that they show you all the computations for every possible book. Has anyone seen the movie Maverick? Well, I suppose it's not my place to recommend movies.
Is that the card and the magician one?
It's not a magician. It's
Or they
just
use the cards to, right?
well, there's no magic involved. It's just a fun old Western movie. It takes place in the 1700s, and it's not Tom Selleck. It's Mel Gibson. He's a poker player. Anyway, it's a fun, cute movie. It feels good. It's a family movie. All right, so keep on going. How many ways can a committee of 4 be selected from a club with 12 members? So just looking at this, the first thing we need to notice is that it's a committee, so there are no positions, there's no order. So this is a combination, not a permutation. So we know it's a combination, and we're saying out of 12 people, choose 4, so the answer is 12, choose 4. And I'm just going to write these down. You can type them into your calculator and see what the actual number is. So likewise, for number 25, how many ways can a committee of 4 people be selected from a club with 10 members? Again, out of 10 people, choose 4 of them and put them on a committee. In no particular order. Now this one, it says the police have 9 suspects. How many different ways can they select 5 for a lineup? Now I think this question is a little misleading because if you do a lineup, you might think that order matters. But in terms of the person looking at them and saying that was the person who mugged me, or that was the person who brought my house, it doesn't matter what order you put them up. They're just all standing up there. So again, out of 9 people, choose 5 of them to put up against the wall. Order doesn't matter. You can all cross out 27 and 28. Do any of you want to go try playing poker now?
Shall I do this class?
Yeah, there you go. Just go back in time and play poker the whole time. All right. Now, these next set of questions are very important. They're just going to help us distinguish between what are we talking about permutations and what are we talking about combinations. So everybody remember, oh, let me put my card there now. So NCR is so remember, a permutation order matters, and a combination order does not matter. And as we do this, let's write up some key words. Okay? So, number 29, a batting order for 9 players for a baseball game. So would that be a permutation or a combination? It's a batting order. So you're saying first he goes up to bat, then she goes up to bat, then he goes up to bat. Does order matter? Order does matter. And in fact, they even give us the key word order. So this one is definitely a permutation because they use the key word order. They're putting them in order. This person bats first, then this person bats. How about number 2? An arrangement of 4 people for a picture. It's an arrangement. So you're having the 4 people stand up to get their photo taken, and you're putting them in a particular arrangement. You know, like the tallest person in the middle, for instance. That matters a lot to people. If the taller person's in the middle or on the sides. So again, order matters, and the word arrangement is another word for order. So that's also a permutation. How about a committee of 3 delegates chosen from a class of 33 students to bring a petition to the administration? The key word here is committee. Is that a permutation or a combination? That's a combination, because committee is one of the key words. There's no order on a committee. A selection of a chairman and a secretary from a committee of 17 people. Now,
We see the word committee. We got excited. We're like, this is a combination. Well, look what we're doing. We're selecting a chairman and a secretary. And those are particular positions that people hold. And so whether you're saying Bob is the chairman and Susie is the secretary, or Susie is the chairman and Bob is the secretary, that matters a lot. Order does matter there. So this is a permutation because you have positions. So I'm going to put the word positions. So far, keywords for permutation are order, arrangement, and position. The next one, a sample of 9 items taken from 74 items. The keyword is sample. If you just have a sample of 9 items, are they in order or not in order? What do you think, Simone? Yeah, they're not in order. A sample is just like a bag with stuff in it. Here's a sample. It's just a bag. So a committee, no order. A sample, no order. A group is another keyword that means no order. So that's a combination. Spices taken from 8 spices on a spice rack. What do you think about the word blend? You're going to take them all, put them in a bowl, and mix them all together so that they're completely blended up. Does it matter what order you put the spices into the bowl if you're just going to mix them all up? No. So that's also a combination. That's a blend. So you have a lot of keywords there that imply order, such as arrangement and positions, or no order, like committee, sample, group, and blend. All right. These are some fun ones. By the way, what do we have left here? Oh, okay. There's an okay amount left. I did cross out some problems, but let's just see. All right. Okay. If you toss 5 fair coins, in how many ways can you obtain at least 1 head? Now, this is a very different type of question. You're going to toss 5 coins, and you want at least 1 head. So how many heads could you have? You have 1 head, 2 heads, 3 heads, 4 heads, or 5 heads. The only thing you can't have is no heads. So what are we saying then? We're going to toss a coin 5 times in a row, and I want to know how many ways can you get at least 1 head. So that would either be head, tail, 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 tail. That's one possibility. Or tail, head, tail, tail, tail. Or so on and so forth. It could also be head, head, tail, tail, tail. So as you can imagine, there's a lot of ways that I can write down the H's and T's in which I have at least 1 head. So here's how you would do a problem like this. In fact, these 3 problems are very similar and they're interesting. How many ways can you obtain at least 1 head, meaning 1, 2, 3, 4, or 5 heads? What you do is you change the question and you say, how many ways can you obtain no heads at all? How many ways to obtain no heads? So what do you think? First of all, how many ways can you get no heads at all? What combination would I have to write down to be a 5 coin flips and there's no heads? What would it be?
All tails.
They're just all tails, right? And how many ways can I write down T, 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 T?
Once.
Just 1. Okay, so there's only 1 way to write down with no heads. Second question, what's the total number of ways of flipping 5 coins? What's the total number of ways of flipping 5 coins? So if you had, I'm going to go back to here. How many ways can I flip the first coin? 2 heads or tails. How many ways to flip the second coin? 2 heads or tails. So by fundamental counting principle, we have 2 to the 5th, which is 32. So there's 32 different ways to write down H's and T's, okay? And only one of them is going to have no heads at all. So I want you to notice how I'm about to write down this formula. I'm going to write the total minus, well, what you don't want. Because if you take the total number of things and take away what you don't want, you're left with what you do want. So in this case, there were 32 different ways to flip 5 coins, and there was only 1 way to write down what you didn't want, which was no heads, and therefore there are 31 ways to flip a coin 5 times and get at least one head. So this is interesting. This is a subtractive method, where instead of directly trying to count what you want, you count what you don't want and subtract that away from the total. This is kind of like when we're talking about odds. When you talk about the total of things that you have, your total is going to consist of things you want and things you don't want. And sometimes it's easy to count what you want, but sometimes it's easier to count what you don't want, and then just subtract. So let's try that again. If you toss a coin 6 times, first of all, let's write down total minus what you don't want. So what's the total number of ways to flip a coin 6 times?
32.
That's 5 times. It'd be 2 times itself 6 times, because you're flipping the coin 6 times. You have 2 choices for each one, so 2 to the 6th, which is 64. So the total number of ways of flipping a coin 6 times is 64. And then how many ways can you obtain at least 2 heads? So that means you want 2 heads, 3 heads, 4 heads, 5 heads, 6 heads. What don't you want? 1 head. Yeah, 1 head or no heads. We're looking at all the different possible ways that you can flip 6 coins. And then you're going to flip out the number, or take out the number of ways you got no heads, and then take out the number of ways you have 1 head. And then what you have left over should be all the different ways that have at least 2 heads. So how many ways can you write down no heads at all? Just 1 way. There's only 1 way for that to happen. Now, how many ways can you get only 1 head? I don't want to write them all down, but it could either be that the first position is a head, and then tail, 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 tail. Or the second position is a head, and then tail, 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 tail. Or the third position is a head, but yeah, third position is tail, tail. So how many? 6. There's 6 ways that you can just have 1 head. And so, there we have it. There were 64 total ways of flipping a coin. You take out the 1 way of getting no heads, you take out the 6 ways of getting 1 head. And then what you're left with, 64 minus 7, is 64 minus 7, yeah, 57. And so there are 57 ways to flip a coin 6 times and get at least 2 heads. Let's try that one more time so we all know for sure how to use this method. If you toss a coin 4 times, or if you toss 4 fair coins, so we're going to toss 4 coins. So what's our total then? You have coin, 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 coin. 2 options each, heads or tails. So we have 2 to the 4th, which is 2, 4, 8, 16. So there's 16 different ways you can toss a coin 4 times in a row. How many ways can you obtain at least 1 head? So what we want is at least 1 head or more. So what don't you want? Yeah, no heads. Here, it might be helpful to write it down. So what you want is 1 head or 2 heads or 3 heads or 4 heads. Because you're flipping 4 coins, so it could be anywhere from 1, 2, 3, or 4. So what you don't want is no heads. So how many ways can you get no heads? That would be if you literally flipped tail, 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 and there's only 1 way to do that. So again, you'd have total minus what you don't want. And your total was 16, and there's only 1 way to get what you don't want, and so the answer is 15. Again, this was a really interesting approach, because instead of trying to count what you wanted, you counted what you didn't want, and then just subtracted that out from the total. All right, let's see. I have a grab bag of word problems here. How many 5-card poker hands consisting of 3 aces and 2 kings are possible with an ordinary deck? So how would we go about doing this? We're going to make a poker hand, and first thing we want to do is grab 3 aces, and the next thing we want to do is grab 2 kings. So how would that happen? Let's look at the 3 aces. How many aces are there to choose from? How many aces are there to choose from total? Yeah. So the first thing we're going to do is, out of 4 aces, choose 3 of them. And then we want to choose our kings. And so out of 4 kings, choose 2 of them. And that's it. That's all the different ways that you'd be able to put together a hand in which you have 3 aces and 2 kings, which, by the way, is a full house. You have 3 of one and 2 of the other. So that particular pair, 4 choose 3, that's 4 times 6, which is 24. So there's 24 unique hands that's a full house of aces over kings. The next one, a bag with 7, it's always helpful to write this out. So you've got 7 apples, you've got 5 oranges, and you're going to choose 6 pieces of fruit. You're just going to reach in and grab 6 pieces of fruit, ignoring the fact that you can probably all tell the difference between an apple and an orange. Then how many ways can you get 6 apples? So what that means is, so the first thing you do is out of 7 apples, choose 6 of them. And then out of 5 oranges, how many of them do you want to choose? Yeah, none of them. It's 7. Yeah. Yeah, so multiplying those out, that's 7 times 1, which is 7. Oh, by the way, we're going to cross out 41. I have the answer on the packet, but let's cross it out. Now, number 40 is another really good and interesting one. A license plate consists of 4 digits. Okay, that's it. So everyone draw that out. You've got a digit, a digit, a digit, and a digit. And how many digits are there total? How many digits are there? 10. So a license plate consists of 4 digits. How many different license plates could be created having at least 1 digit repeated? So what would that look like? We want a license plate with at least 1 digit repeated. So we would want the license plate 8857. So at least one of them is repeated. What we don't want is all different numbers, like 3418. Okay? So let's make a note of this right now. What do we want? We want at least 1 digit repeated. Right? So therefore, what do we not want? How would you describe it? What do we not want? Yeah, all different. And what they're asking us to do is count how many different license plates would have at least 1 digit repeated. Well, that would actually be very hard to count. Because you could either have 1 repetition, or you could have 3 of a kind, or you could have 4 of a kind. And that's mind-boggling to think of all the different ways that you could have 2 of the same number. You could even have 2 pairs, right? I mean, there's so many different possibilities to consider. It would hurt the brain. So instead, again, what we would do, instead of counting what you want, you would count the total minus what you don't want. Because that would give you the same result. So first of all, what's our total? How many different license plates are there? Is it 10 times 10 times 10 times 10? Does it have 10 options for a digit? That's the total. So that's 10 to the 4th, which is 10,000. So there's 10,000 different license plates available. Now what about what we don't want? We don't want them to be all different. So how would we compute that? What does that look like for them to be all different?
So how many choices do you have for the first one? Yeah. But now, whatever you just chose, you're not allowed to choose it again. So how many choices do you have for the second one? Only 9. And again, whatever you just chose, you can't use it again. So now you have 8, and then you have 7. So now we multiply that together. Is anyone have that? 10, 7. Oh, it's 5,040. So there's 10,000 total ways. There's 5,040 ways in which they're all different. And therefore, if we subtract that out, then there will be 4,960 ways with at least 1 repetition. And you can cross out 41. All right, so where does that leave us? You can also cross out 42 and 43, just to be, just to round that out. So that leaves section 8.3. There's a couple problems left in 8.3, and I do want to do a couple of them, but to be honest, we don't have to do a ton of them. So we'll just wrap that up when we come back next time, because I know class is over. Well, it's almost over anyway. So you can do all of section 8.1 and 8.2 when you go online to do the homework. What's that, Steve? No.
Yeah.
So for the homework, you should at least go ahead and do 8.1 and 8.2. And I also scanned all of the solutions, so I'll post all that on Canvas tonight. And Sally was here. David was not here. I can't believe it. Oh. Wonderful. I think I've given you everything you need. Oh yeah, I'll post the practice test online as well. That way you have all the solutions and the practice test. Good idea there, Luis.